Oh, boom. Squeeze in. Okay. Okay. I'm reminding that if you're sitting in the back and you can't see, you can join us on Zoom and see it on your own laptop if it's easier for you. I have no idea. No. Before we start, I want to ask who here has taken a course about neural networks? Only you two? Oh, Romy as well? Okay. Who here? Okay. And you two will be taking a course next semester. Okay. No. Okay. The reason I'm saying is because we are going to be talking about artificial neural networks, which are the modern machine learning part. Like it's what's most popular today by far, for 3 weeks. So this week, next week, and the last week. But obviously, we're not going to be able to cover a lot of things. There's a lot more to cover. What I will try to do is from time to time just mention things that you guys can learn by yourself later or read up online. I want to give just the foundation, just the basics, okay? I personally think neural networks is the most important part of this course. So if you don't remember anything, you don't care about anything you learned until now, start paying attention now and you will succeed, okay? Yeah, so that's a good question. Let's talk about why they're called neural networks, and it's not a good name. When over 100 years ago, it was discovered that neurons in the brain talk to each other. They're connected with the axons to dendrites. We know this. And so they can form some neural network. People in the machine learning community, we can talk about it, how the history, if you're interested, said, oh, okay, back then it was very popular to, telephones were a new invention. So like, oh, it's like a telephone center that, people communicate to each other via telephone. That's how the neurons work and so on. And then they started building all these theories of how these neurons can communicate information to each other. And so, and that's how it is. And then from the machine learning side, they did a model of a neuron, or a model of many neurons, which transmit information one to the other, and they called it a neural network. But we can talk about, if you want after class also, it's maybe a little bit similar to how actual neurons in the brain work, and maybe it's not similar at all, we don't know. But the name kind of stuck. So in neuroscience, they're trying to say artificial neural networks are the computer models, the machine learning models that learn stuff, and biological neural networks are the actual ones in the brain. I don't know if people really, sometimes people say ANNs versus BNNs, artificial versus biological. I try to say artificial neural networks when I'm talking about the computer, the machine learning ones. But if I just say neural networks, I probably mean the machine learning ones, okay? Because this is not a neurobiology, neuroscience class, okay? You know what, we can talk, if it's interesting, we can talk later, how much is it similar to the brain or not, or, okay? We can talk about it. Okay, but the name has stuck. Let's do a quick reminder. Who remembers how a linear regression looks like? We have our, can we all see the board? Yeah. We have our Y predicted, which is linear regression. Let's say 2 features, X1 and X2. Yes, so you can, so I wanted to spell it out a little bit nicer. So we can do the B0, which is the bias, plus B1 times X1 plus B2 times X2. Everyone remembers this? and we have to find three parameters, B0, B1, and B2. No, this is a second one. It's X1 is, I don't know, height and weight, and you want to predict their, I don't know, health or something, okay? Excellent. And then, like Asaf said, people don't write this out anymore. They do like, I can do it in a new line, so we just remember. We write big B, which is a vector of all the weights, times big X, which is a vector of all the features, right? And then you get, this is understood, so on. And then this is a linear regression, but we also have a generalized linear regressions, generalized linear models. What is the difference? JLMs, yes. What is the difference? What's the addition? Exactly. There's a link function or an activation function, which just goes here. Yeah, so this is a, I like to call these activation functions, but it's the same as a link function, okay? So what can the link functions, Noah, you mentioned sigmoid is one of them, and there are many others, right? Okay, so this is clear so far. Now, we can draw a representation of this GLM, which is this. We have X1 and X2. We're just putting them on one on top of the other, it doesn't matter. Okay, and then we have, this will be, not yet, not yet. This will be the B times the X's, right? Oh, and I forgot to mention the connections. We put the B's on them. I'm gonna make them smaller. So far, I'm not giving any new information. I'm just representing the formula that we wrote above in a visual way, right? This is B1 because it goes with X1, and this is B2 because it goes with X2. So that's a good question. B0, we can put it right here, that it goes here. Or, yeah, so there are two ways to think of B0. We can always either add it here differently, or we can always say X0 will equal 1, and then B0 times 1 is just B0, right? So it doesn't matter, you can do both ways, okay? I'll just draw it this way. And then we take this B times X, and I'm using a square because that's to show that it's different. And in the square, we do some activation function, right? And then we get out of it the Y, or Y predicted. Is this clear how these two things are the same? Yeah. Okay. Then, and if our activation function is the sign function, remember positive, negative, then this is called the perceptron. Remember that? Yes. And then people said, oh, this is exactly how the brain works. There's neurons that send information, and then there's a neuron that receives all the information in the dendrites, right? And then it sums it all up. It applies some nonlinear activation function. What? Yeah, it applies some nonlinear information with a threshold. Would it fire? And then it either fires or not fires, kind of like a sign function. It's either positive or negative, or maybe, yeah, sigmoid. It's maybe 0 or 1 or something like that, right? And then someone said, wait a minute. This perceptron can't solve the XOR problem, right? And I think you all had to homework about it, showing that it can never solve the problem of saying if either one of them is 1, or either one of the inputs. And it also can't do a lot of things, but our brains do this all the time. So this is not a good model for the brain. Okay, so what did they do? What exactly? So the idea is to add more. We can think of it as two ways: either add a relay station in between, okay, or many relay stations before we get to Y, or we can just say we add more nodes and then we get to Y later. Okay, it's the same thing. So instead of drawing the whole thing, I prepared ahead of time a picture. Where it goes from 2 X's to a middle relay station. Okay, we're gonna analyze this photo now. So what happens here? it goes from two inputs, x1 and x2, into three different, we call them neurons or activation units, in a hidden layer. And each one has its own set of three parameters, three b values, right? And then we apply a non-activation function on all three of them. And then we take these three new values and we multiply them by new parameter. These beta values are completely different than these beta values. And then we get the linear summation and a non-linear activation, then we get y, okay? If you, just terminology, this is the input layer. It's also called the zero layer. And then this is the B0 matrix, which has all the values that get multiplied with the zero layer. And then this is a hidden layer, layer 1. And this is output layer or layer 2, right? This is B1 matrix. And then each weight gets numbers by what it connects to where it connects to. So this B0 means it's multiplied by the 0th layer, the input, and goes to 1 because it goes from x2 to this new hidden layer 1. So from the second neuron to the first neuron. Okay, is that clear? Excellent. If you want to do the matrix multiplication, you can see it's very clearly 1 by 2 and then 2 by 3. So you get a 1 by 3 and then you do 1 by 3 on 3 by 1 and then you get a 1 by 1. So the matrix multiplication works out. Now, I just want to show you, because I have it in the picture as well. You can break it down. So this is just the definitions of each part. So let's work. Okay, it works somewhat. I might not keep this. So this is just the definition. So we look backwards. So y is the z2, which is the, oh, I forgot to say, I chose the hyperbolic tangent, which is the tan h, as my nonlinear activation function. I could have chosen a sigmoid. I could have chosen other activation functions. Okay, so y is the tan h of the z vector, which is the hidden layer, times the b1 weights, right? And then this is described as this. And so essentially, I'm just breaking it down. And then, okay, so it's clear what these formulas show. These it's a nonlinear activation function, hyperbolic tangent. It's like you have cosine, yeah. So there's one hyperbolic tangent. That's what it's called. Okay. It's the opposite of the tangent. Okay. Okay. And then the important thing that I want to show is that then you can put it all back up and see the relationship from y back to the x's, and we see that because of this intermediate unit layer, the relationship gets very complex. Y is the tan h of beta 11 times tan h of beta 11 x1, right? So the x1 features get used a lot of time, okay? So you can think of this as one big GLM of GLMs, right? It's like not a GLM, inside of it more GLMs or something like that, right? And that's a very good way to think about neural networks, as stacked GLMs or nested GLMs, okay? Is that clear? Awesome. In this paper, in this example, I also have it in matrix form if people like to do the matrix multiplication and see that works out, but I'm not going to bother you with it. Okay, why is this? Oh, last thing I want to say, this network is called a fully connected neural network. Why? Yeah, because every node is connected to the other nodes, all the other nodes in the next layer, okay? So this is a fully connected neural network with two features, x1 and x2, one hidden layer of 3 nodes or 3 neurons or 3 units or 3 hidden units, and a tan h hyperbolic tangent activation function. Okay? Can we build a different one? Can we add more layers? Of course, right? Nothing's stopping us. Who knows how many hidden layers does GPT-3 have? How many would you guess? So they don't tell us. It's a trade secret, but it's expected 90-something layers. Okay? Yeah, GPT-4 has even more hidden layers. Okay. Yeah, it's considered a lot. So what I'm going to show now is that, okay, how many parameters do we get? So just to compare the linear regression, we had 2 inputs, so we had 3 parameters, right? That's always. But now we have 2 inputs, but how many parameters we have here? I think if you count, it comes up to like 12 or 13. But imagine if we have more layers, so it multiplies by how many? And also we can have larger layers, right? We don't have to have a layer of 3. Why 3? We can go a layer of 10, right? And just adds a lot more parameters.
And this is just 2 inputs.
This is what?
Just
2 inputs, right? Imagine if you had an image, which is, I don't know how many pixels. It can be thousands of pixels, right? It's a good resolution image. Yeah. So how do we learn all these parameters? What do we do? Train. How do we train?
You start with the
Yes. So what is that called? Backpropagation. Chain rule is, yeah, but we have a different name for it. Backpropagation is you backpropagate over something. Gradient descent is what I was looking for, right? Gradient descent. So we all know what gradient descent is. So I'm taking here the words of Sam Altman, who's the CEO of OpenAI that gave us GPT, and he literally just said, gradient descent can do it, guys. Don't worry. It will take a lot of computing time because you need to learn a lot of parameters. Gradient descent can do it. So what is gradient descent? We know how to do gradient descent for our regular GLMs, right? You start with random weights. You have the loss function. And then you take the derivative of the loss function to see for each weight, does changing it a little bit make the loss go up or go down, right? Because that's the slope of the loss function or the derivative of the loss function. And then we change each weight by its step size to make the loss go down, right? Excellent. So this is exactly what we do, except here we're going to do it in steps. And this is why it's called backpropagation. We don't update all the weights at once because there's so many weights, so many betas that we have to do. We first, we put in our data and we go forward, we multiply, we do the whole thing, we get our Y. We compare our predicted Y with the actual Y to get the loss function, right? To get the loss, I'm sorry. And then we go backwards. We update the last layer's weights first based on the derivative of the loss function with gradient descent. And then we update the layers beforehand and the layers beforehand and the layers beforehand. Okay? Excellent. Now, you might say, oh, this is going to be so difficult because let's say I have a neural network with 100 hidden layers. How am I going to update the first ones? I'm going to have to take the derivative of the loss, which, you know, the Y is all the way at the other end, all the way in regards to the first weight. So what happens? Exactly. So thank God there is the chain rule. Wait, I have a picture first that I wanted to paste, which shows exactly this. So this is how it works. This is a neural network with 2 inputs and 2 hidden units, and then the loss. So you do a forward pass, which means you put your data in, you get your Y, and you calculate your loss. I think this is root mean square error. I think so. Yeah, because you do square and then root. Okay. And then you calculate the loss. So you do the derivative of the loss function with regards to this Y. And then the derivative of the loss function with regards to this Y, okay? To this W6 weight. And then the derivative of, let's say, the W2 weight in regards to to Y2. And because of the chain rule of calculus, which I'm going to remind everyone what it is, let's say I have a function Y, which is a function of a function